Looks like a rocket engine. In a previous video, I described how an annular magnetic field might be used to help extraterrestrials fly through space using an ion drive. And here's some images of it. You have some crop-drawn images in the center and on the right. You can see a Corbino disc, which is just two tubes, negative on the inside, positive on the outside, with a current between them. And that lies inside of 6 electromagnets, which make an annular magnetic field. When you add argon gas, it gets ionized and it spins inside and gets shot out somehow. Now, in order to understand the physics, I've actually built a model of that. You can see here our annular magnetic field made of permanent magnets, 2 tubes, negative on the inside, positive on the outside, just like in our crop drawings. And we have a red lead on one tube, a black lead on the other, plus or minus 40 kilovolt DC. And we're going to make the gas spin, the argon gas, and we're going to watch to see if it's shot out and try to understand why. This is the very basis for space propulsion, and it could replace chemical rockets if it's strong enough. So it's very important. Let's get into the experiments. Now, when we add argon gas and electricity to this device, you can see a fast spinning ionized plasma in the empty annulus between those 2 tubes. Negative inside, positive outside. Now, in principle, the spin velocity of that plasma can be converted to thrust. Now, it's well known, if we have a Corbino disk, which is charged minus on the inside, plus on the outside, that ions will spin very rapidly through its center. For example, these argon ions that are coming into it and then spinning, because there's what's called a radial-magnetic field. South poles around the outside and north pole in the center. So, due to what's called a Lorentz force, which everybody knows who studies physics, the ions will spin very rapidly. But could there be another force to shoot it upward? Well, if you look closely at a radiomagnetic field, you see there are also big vectors for south to north pointing inward in the plane all around the outside. Like that. The annular radiomagnetic field, and that's what we see here. So there's an additional Lorentz force of the same kind which can potentially make the argon ion shoot out due to all those inward pointing vectors. And you might think this is novel, but it's really not. What's an astronomical jet? You see matter spinning very fast around a gravity field and then shooting out vertical to the plane of spin, just like in our crop drawing, or the models will show soon. Now, physics on paper is interesting, but really means nothing. For that reason, we're going to test 3 different models to examine these new ideas closely. We're going to have a small model, an aluminium tube, with this piece of copper tube inside, a medium model, and a large model with bigger aluminium tubes with a different piece of copper inside. And for our annular magnetic field, we're going to use various devices. They'll typically be like this: a stack of 6, 8, or 9 magnets, 4 each, held together by perspex and screws. And they provide a magnetic field not only vertical up and down through the plane, but also inward everywhere we go around. So we should get 2 kinds of Lorentz force from this particular magnetic arrangement, which will make the ions not only spin, but eject. And when we place that annular magnetic field around the 2 tubes, 6 stacks of permanent magnets, 4 in each. The 2 tubes are minus 40 kilovolt DC inside, plus 40 kilovolt DC outside. Add argon gas gently. Turn on the power. You can see the current between the two tubes begins to spin rapidly around the north pole of the magnetic field. Argon ions inside, electrons outside. This is about 120 watts. You can see a blue glow from the argon gas at the bottom, but not much is being ejected. And the reason is this field isn't long enough to go beyond the end of the tube. It has to go a bit further. So for that reason, we made several other magnetic fields, and we'll show them to you now. I made a longer annular magnetic field using 8 bar magnets. Let's turn on the electricity and see what happens. First it starts spinning, and then as we go higher, the spin velocity may be converted to thrust as we bring the magnetic field forward to encompass the end of the magnet. You see very clearly it's thrusting outward. That's called the annular railgun. You see the blue color of argon gas being released. I've put a long radiomagnetic field of the opposite polarity around these two tubes. As we turn on the power, you can see it spinning very fast clockwise the other direction. As I bring the magnetic field just a little bit forward, you can see very clearly how gas is coming out in all directions via Lorentz force. Now for this first small railgun, we just used 3 parts. An aluminium tube with a copper tube inside of it, 1 red and 1 black 40 kilovolt, and that's the Corbino disc. And then we have a stack of magnets, 6 stacks, 4 each, to make an annular magnetic field, which resembles this crop picture surrounding the Corbino disc. When we add argon gas, it gets ionized, goes into it and spins and gets shot out by what's called the Lorentz force of magnetism. What happens is the spin velocity goes like that. See, it's spinning very fast. And then these magnetic fields all point inward or outward around the outside in a radial sense. The magnetic field is here, 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 like that. So as the spin goes past it, that spin velocity is bent sideways and shot up as thrust. Spin, then shoot up. Spin, and then shoot up. If you don't understand this, just study some classical magnetism and electricity. Now for a larger version of this device, we have to use angular magnets. We can't use just radial ones. Here are 8 of them in a circle, and you can see how spinning argon gas is being shot out periodically from a 50 centimeter wide tube and 25 millimeter wide copper tube inside. Should we call this the ion propeller? It spins very rapidly, and then the spin velocity is shot out as argon gas exhausts. This device also works with a permanent ring magnet rather than angular magnets, which can teach us something about its mechanism. You can see the argon gas being shot out in pulses. Now, in order to get this result, the end of the aluminium tube has to lie very close to the plane center of the ring magnet. Now, why is that? If we pull it back a bit, we lose magnetism. There's in the plane. If we push it forward a bit, we lose magnetism. When we study the structure of that ring magnet, we can see 2 south pole parts, left and right, that make the ring. And the empty space in the middle is an effective north pole, which extends up and down axially. And you can see how the magnetic flux is going through it. Now left and right, at that very center, there's a radiomagnetic field where both south pole parts point into the single north pole part. So it's radial here pointing in, and radial there pointing in, and all around. And that's where we're getting the thrust for argon ions to be ejected outward. When the end of the aluminium tube and copper tube lies exactly in line with that radiomagnetic field. If we extend the argon gas a bit further by putting a plastic tube on the end of the aluminium rod, then you can see an enormous amount of argon ions coming out beyond the end of the aluminium tube, right where there's a radiomagnetic field, and being ejected outward. When the empty annulus of this device gets really large, I'll put a 50 millimeter aluminium tube around 25 millimeter copper. You can still get it spinning like this, but then you have to use 9 stacks of 4 magnets and not just a ring magnet like before when the annulus was very small. Also, for a device with such a large annulus, we have to have a plastic tube extending the argon gas beyond the aluminium itself. Then it spins and ejects quite nicely. So long as the end of the aluminium tube lies within the center of these stacks of magnets, it spins quite nicely with such a large annulus. When I take it out, you see it loses magnetism. Put it back. Spins and ejects quite nicely. When I put the tube ahead of the annular magnetic field, it loses magnetism as well. And then when I bring the field so it's sort of centered on the end of the tube, it again spins quite nicely. Now when we go to higher powers, this device really shoots out a lot of argon gas, this cloud above the end of the tube, even with such a large annulus. Most favorable arrangement with the magnets aligned correctly and a long tube to keep argon gas from being escaped. We got a huge cloud of argon that completely covers the end of the tube. Blue argon gas. So it's definitely being ejected. Everything seems to be working well now. However, we still have one trouble. We're not getting release of the ionized argon gas from the plus and minus electrodes. The Lorentz forces are shooting out, but it's not being released. Now, one way to solve that trouble is to put a little switch in. I've got a hand switch temporarily to shut off the electric power while the ions keep spinning. And that might give release. Let's see what happens. Turn on the power. Start it spinning. Got a lot of big cloud of gas there. And then let's switch the power on and off quickly. When I do that, I can feel a little pulse of gas coming through the end of the tube here. DC power, and then releasing it a little bit with a hand switch. It begins to look like a rocket engine. Argon gas is just covering the whole front of that electrode.